Okay, so in the last video we were talking about the Dirac delta function. And so, um, just as a reminder, the Dirac delta function looks something like this, which is very strange. And now we're kind of scrolling past the properties, but let me summarize those properties just to be sure that everybody's clear what the properties are. So, summary. Of the properties of the Dirac delta function. One is that the Dirac delta function is the limit as tau goes to 0 of d sub tau t minus c. Okay, that can sometimes be very useful. Furthermore, Dirac of t minus c f of t is just equal to the Dirac of t minus c times f of c. And so that has some properties that are interesting. But first, the integral from minus infinity to infinity. Getting ahead of myself, that's the Laplace transform. If I'm just integrating the Dirac delta function, I get 1. And finally, the Laplace transform is e to the minus cs. Okay, and so now let's use the Laplace or the Dirac delta function to solve some differential equations. So to start things off, let's try 6.5, number 2. Now I should say in all of these problems they ask you to draw a sketch, and we're going to draw a sketch here, but generally speaking, for some of these sketches you really probably need the computer to do that. So you should see how far along you can get by hand before you need the computer. And we'll do this as an example. So here we have y double prime plus 4y is equal to delta of t minus pi minus delta of t minus 2 pi. And we also have 0 initial conditions, which means that y of 0 equals 0 and y prime of 0 equals 0. I got a squeaky chair. Now take the Laplace transform of both sides, and we get s squared times y minus 0 plus 4 times y equals e to the minus pi s minus e to the minus 2 pi s. So this one's easy to solve. So you might be saying, geez, Professor Henley chose a really easy problem to do. Well, I chose this for a couple of reasons, not the least of which is to analyze our solution. So remember now when we said that, if we had something of this form, right, this is equal to like e to the minus pi s minus e to the minus 2 pi s times h of s, then we just take the transform of h of s, right? And so if I take the inverse of this, I end up with u pi of t little h of t minus pi minus u sub 2 pi of t little h of t minus 2 pi. And so really, then the only question is to invert h of s. Okay, so we'll remind you how to do that in just a second here. But our h of s is very simple. Our h of s is just 1 over s squared plus 4, which we can rewrite as 1/2 because I need a 2 in the numerator to do the inversion, and now it's all ready. And so the inverse Laplace will be 1/2 times the sine of 2t. Now, just for sake of reference here, this function has period pi. Okay, so now let's write down our solution. Let me keep that as a reminder. Our solution, y of t, is equal to u sub pi of t times this 1/2, where's my 1/2, sine of 2. Remember now, I'm putting the t minus pi in here using this. This is the notation I'm using right here, right? That's why I'm putting it in like that. Okay, and then we have minus 1/2 u sub 2 pi of t times the sine of 2t minus 2 pi. Good. Now, if I were to write this piecewise, what would it look like? Y of t is equal to 0 if t is less than pi, right? And then at time pi, I get 1/2 sine of 2 times t minus pi if t is between pi and 2 pi. And then we get 1/2 sine of 2t minus pi. How many parentheses do I need there? Sine of 2t minus 2 pi. This is a big expression. If t is bigger than, whoop, running out of space, 2 pi. Okay, let's simplify this. So we said that the sine of 2t has period pi. Therefore, what is the sine of 2 if what happens when I shift the function by pi? Well, that's the same thing as the sine of 2t. Similarly, what happens if I shift it by 2 times the period? That's also sine of 2t. Right, so then this simplifies my expression quite a bit. Y of t is now going to be 0 if t is less than pi, and then it's just going to be 1/2 the sine of 2t if t is between pi and 2 pi. And now what happens when you subtract the 2? You get 0 again. Good. So there's our function. So our solution then looks like the following. Up until times pi, the function is 0. Then at time pi, we get our sine of 2t appearing. And then at time 2 pi, the function cancels itself back out again. Okay, so this is the solution to number 2. Good. Now, in a similar way, you'll see some sigma notation being used in this section. So let's just do a quick example here. What would I do if I wanted to solve something like y double prime plus y equals the sum n equals 0, let's just say to infinity, delta of t minus n pi. Well, we do want to be careful with that, right? Because we're adding an infinite number of things together, and I'm not sure if that converges. But since this is a generalized function anyway, we'll just proceed. Let's say we have 0 ICs, and so that gives us s squared plus 1 times y when I take the Laplace transform. And remember that the Laplace transform is linear, so I can scooch the Laplace transform into the sum, and so that's going to be Laplace of each of those, which is just going to be e to the n pi s. Okay, so that just means that y is equal to the sum, n equals 0 to infinity, e to the minus n pi s over s squared plus 1. Good. And then this is pretty straightforward to invert, right? So therefore, y of t is just going to be the sum, n equals 0 to infinity, u sub n pi of t, sine of t minus n pi. Okay, now just like before, there is a way that we could simplify this a little bit, but I'll leave that up to you to look at. I just really mainly wanted to focus on this. What do you do with the summation notation? And so, as it turns out, the sum of the Laplace transforms or the Laplace transform of the sum, is the sum of the transforms. So you can just take the Laplace transform right into the sum. Good. My 10 minutes is up. I will see you in 6.6.